Today's video is all about machine learning operations, or MLOps. It's a set of best practices to help you deploy and maintain your machine learning models reliably and efficiently in production. This is the whole game of MLOps, meaning we'll lightly touch on the different components of MLOps with an example using the Palmer Penguins dataset and R, specifically the tidymodels packages as well as Vetiver for deploying and maintaining our machine learning models. Let's get started. Before we dive into the code, I want to zoom out and look at the full MLOps lifecycle. We're going to assume that data collection is already complete. We're using an example from the Palmer Penguins package. I imagine many of you have seen this data set before. We'll use a little bit of the tidyverse tooling to start understanding and cleaning our data, though that's not the focus of today's video. We'll be using the tidymodels ecosystem to both train and evaluate our model using techniques like cross-validation and hyperparameter optimization with Bayesian optimization approaches. Vetiver is really our workhorse package for today's talk. That and a few packages that go well with it can be quite useful for doing things like versioning our model, deploying our model, as well as monitoring the model after deployment to ensure that it is providing reliable predictions. Each of those steps is quite easy for data science practitioners to overlook and assume that somebody else will handle for us. That's great if they will, but it's also good for us to understand these critical steps to creating value from our modeling efforts. All right, so let's dive into the code. I have a bunch of packages that I'm importing here. I'm going to step through some of them briefly. Tidyverse, I'm sure you won't be surprised at all about. We're using Palmer Penguins and GT. The Palmer Penguins is our data set. GT is for our tables. If you haven't tried it out, I definitely would encourage you to use GT for your own tables. And then we're also using the conflicted package to handle some of the conflicts that pop up with using this large number of packages. We'll be using the tidymodel system and also a few other packages that we need to install such as Ranger for our random forest model that we'll be building, and Brule, not sure how you say it, to create neural networks using the Torch framework. You also will have to install Torch as part of this, so just note that as you're executing this code on your own. For the MLOps portion of this, like the operationalization of our models, we'll be using the pins package for model version control, as well as Vetiver, as I already mentioned, to create the API, and we're creating a plumber API, which is why we have that package as well. I'm also setting a couple of defaults here. These are useful to handle things like conflicts and ensure that the tidymodels printing matches the theme that I'm using. So specifically, I'm using a dark theme, so I want my messages to come out as dark. All right, so let's jump into the exploratory data analysis. As you see on the screen here, you should probably do more than this for your own modeling work, but this is a fairly well-known data set to myself, and I'm sure many of you as well. We're going to be plotting here the flipper length versus the bill length. The model output that we seek to predict here, we're looking at a classification exercise where we want to determine if given features like flipper length, bill length, and body mass, can we predict if the penguin is a male or a female. Plotting flipper length versus bill length, you see that there's some clear differences by sex. This is faceted by the penguin species. So this seems like it's a reasonable task that we could model fairly well here. We want to prepare our data set. You'll hear Julia Silge during her screencast talk about spending your data budget. This is one way that we can do that by creating a training and test split using the convenience features built into tidymodels. So the first step here is we're going to do a little bit of cleanup. So we're going to drop anything in any of the rows where sex is NA, and we're also going to toss out year and island because we're not going to include that in our model. We then can use the splitting feature. So initial split is another convenience function to split into our training and test set. And we're going to stratify this by sex here. So we can give ourselves a good chance of having a balanced training and testing set. Another important step here for model evaluation is to use cross-validation, and we're just going to use some v-fold cross-validation, again using these convenience functions. So with 15 or so lines of code, we've largely prepared our data set and we're ready to get into the actual modeling stage. Okay, for a little bit of feature engineering here and reproducible feature engineering, we'll use the recipes package. This allows us to add new data and apply the same transformations that we did to our training set, and is a great, if you haven't used recipes before, I would strongly encourage you to integrate these into your machine learning workflows. We're going relatively simple here, but this does give me an excuse to show off code annotation within Quarto. That's what you've been looking at here. So the first thing that we're doing is we're defining a recipe where we have sex as the output or our target, and then all the other variables we're using to predict the sex, the penguin sex, and that period placeholder is the way that we do that. Of course, we're using our training data. Next, we want to apply a transformation to correct for any possible skewness within our data. The Yeo Johnson, again probably butchering that name, is a good method for that. And then we want to take species. This is a nominal variable input that we have, and we're going to create dummy variables from that. This does require, based off the way we're doing it here, that all predictions need to be using the same species that we had in our original training set. And then lastly, we're going to normalize all of our numeric predictors. Each of these steps are pretty much no-brainers if you're doing some of your own recipe building here. If you want to learn more, I encourage you to visit the links at the tidymodels website, or looking at the Tidy Modeling with R book that I found quite useful in my own experience. Okay, so now we're going to get into actually specifying these models. The first is logistic regression, just about as simple as it can be. We're using some L1 regularization with this penalty value here, and then we're going to be using the GLM engine for the logistic regression. So quite simple, nothing to tune here, no hyperparameters for us to optimize. So let's jump on to the next one, which is a random forest model. This is why we need to install the Ranger package or load the Ranger package. And we can specify this with the, we're going to be tuning one parameter, this min in that you can see here. And the logistic regression classification, that was implied, but we do need to set it explicitly in this case using for our random forest model. So we have logistic regression, random forest, and then we'll add one more using the, we're going to be using Torch to create a neural net. This has a few additional hyperparameters that we can tune, things like the number of hidden units, the number of epochs that we want to train for, a penalty value here, as well as the learning rate. So this is beyond the scope to talk about the different components here, but part of tuning all of these, part of the reason to do so is just to demonstrate the hyperparameter optimization as part of a model building exercise. We'll be using the Brulee, again butchering the name I'm sure, package that allows us to build, to use these Torch neural net models. So pretty cool. There's no Python dependency using this, and you'll see that it works quite easily. And again, we're setting the mode to classification here, much like we did with the random forest model. Before we actually go and fit our model, I do want to specify some parameters for hyperparameter optimization, and we're going to be using the Bayesian optimization approach for this. We have 4 settings for this. The first, no improve. This means that we can go up to 10 iterations without any improvement before the training or the optimization will halt. We do set a time limit of 20 minutes. And then these other 2, the saving prediction, this is useful if you want to go and actually plot the predictions from the different models that you're fitting throughout for in many cases, you can just set that default, but it can be, again, useful if you want to compare different models to each other. And then lastly, the verbose equals true is useful if you want to see how the hyperparameters and the model performance is changing throughout the fitting process. I recommend doing that if you're going to be fitting a lot of hyperparameters or it takes a while for the model to fit, just so you can monitor the progress as it goes. We can use a package called workflow sets. This is part of tidymodels to actually fit all three models. So our logistic regression, random forest, and neural network all at one time, or all with one function call, that is. And we also can actually use the workflow map function from workflow sets to do this with cross-validation. So we created those cross-validation folds when we were creating our training and test splits. And we can use those here for a maximum of 50 iterations. So this, with just a little bit of code, you actually can fit a lot of different models with that. And really, it's limited by how long you're willing to wait for this to complete. So executing this code, I think, in my experience, it took about 15 minutes to fit based off the code that I've showed so far. So just keep that in mind as you do this on your own. I've already run this, and so we can look at some of the different model performances here. We're specifically looking at the area under the curve of the receiver operator characteristic, or ROC curve. That's our main metric that it's using in order to select models. And we can see that it's showing the best model performance for each of the model types. You can see a graphical version of this using the auto plot function, another convenience of the tidymodels framework. And we actually can see that for the area under the curve, many of our models are quite similar to each other. So actually, what I would recommend in this case is, although our neural net does manage to eke out technically a higher average area under the curve for the ROC, I would actually recommend selecting the logistic regression, given its simplicity and interpretability of a model, with the overall performance being marginal between all of them. So we'll use the recipe GLM as our model ID to go on to finalize this model. So for to finalize, the first thing that we're going to do is extract the workflow based off the model ID that we set on the previous slide there. And it's going to, in this case, we're selecting the most accurate of the model. You really could use either one. This is just showing an example of one here. We then want to update our workflow based off the model that we just selected. So you can see we're using extract workflow and finalize workflow, starting from that original workflow set object. And then finally, we want to fit our data from this final workflow that we just created. And instead of fitting on only the training set, we want to fit on both the training and the test set. Because this is a logistic regression, it fits quite quickly. And we can see that the overall accuracy from this combined data set is expected to be about 90%. With the area under the curve of about 97 here. So you can see a plot of what that looks like. If you're new to these, you want the sensitivity versus the 1 minus specificity plot. You want this to be as close to a 90-degree bend here as possible. So this looks acceptable enough for a simple tutorial here. So we can go ahead and proceed on. All right, so now that we have our model in hand, the next thing that we're going to do is create a Vetiver model using, unsurprisingly, the Vetiver package, and also to create an API. The first step here is just to extract the workflow object from the final fit that we just performed, and we can actually directly create the Vetiver model from that. We're going to give it a name of Penguins model, and then we'll use the pins package to pin our board to a local folder, just a directory that I've called pins.r, and we'll actually use a versioned model here. That way we can go back and compare our model, or how the model has changed over the different versions by saving that model, and see how it would perform over time here. Now, I do want to note that you can create the plumber API after writing the board, sorry, I skipped this line 6 here. So we create our model board and then we write our model or pin our model to this board using some convenience functions within Vetiver. And then we want to go and create our Plumber API. So I have this note here that we do need to modify the Plumber API in order to deploy it to our target destination, which today is Huggingface. I'll talk through where and why we had to do that in just a moment. And then I'll also show you an example of you can do boards all over the place. There's a lot of flexibility within the pins package, and I'm writing a board manifest. This basically is much like a passenger manifest, lists the models that are in the board, which will allow us to actually use GitHub as a model board for us, which is quite a convenient. It is quite convenient and something that I learned in the creation of this video. Okay, so in order to do this, we do need to, for all of the code that I've run so far, we need to take the models that we've pinned. So we've pinned all of these locally. Again, it was set that pins are folder. And we need to push those changes to our GitHub repo. I'm using so it's in my GitHub under r-MLOps. When I push these changes, I can now use the board URL functionality from pins and directly use the model that's pinned to my repo. This allows me to separate out the API deployment from the model version control, which is a recommended best practice overall. So we can use this location. I'm just using a helper to specify the GitHub raw or the raw user content location, so I don't have to remember it. And then we set up our board using this board URL, and it works again because we wrote that manifest. The manifest is in the form of the _pins.yaml. We can then what didn't work here. So I have this note here. This code actually did not work. What I wished would have been able to work was to have the model board there and write the plumber directly. Because this didn't work, I got an error about the board not being parsable. And because of that, we need to take the original plumber.r code that was written for the local board and update it so that it can use the one that's stored in the GitHub repo. So rather than speak abstractly, let me show you exactly what I had to go and change here. So most of the code did not have to change at all. This is specifying the libraries that we need for the API, as well as the modeling libraries in order to make the prediction. So relatively simple. This controls a lot, this does a lot for us, and produces this API that we can then go and call later. And to get this working for the model that's hosted in GitHub, the specific changes that I had to make were right here. So I'm setting up that pin location as being in my GitHub, and then I'm using this board URL like you saw a few slides ago, and then we can read the Vetiver model from that board that matches this penguin model name. I don't specify a version here, though we certainly could. I believe it will just inherit the latest model version if you don't specify one, so that's why I left mine there. So I'll jump back to just compare the difference here. The original one was using the local board folder. This would not work unless you were to deploy your model with your API. Using the approach that I have here on line 15 through 17 allows us to separate out the API deployment from the model version control. Okay, so the final step that we needed to do here was to create a Dockerfile that we will use to host this API on Huggingface. Here is the Dockerfile that's generated by the Vetiver package. I believe it's Vetiver write Docker. And I do have to make a couple of changes just to make it work within Huggingface, like I mentioned. So there's all the different features there. And to zoom in specifically on what I had to change, a couple of things here. I now run the Docker as a user. So I added a user called app user, set the home location to be this app user directory, and set my working directory to home. The other changes that I made is I created the pins cache location inside of this home user directory and set it so that the app user, so the user running this Docker container, would own that location. And then I did it again to have the specific location here as well. As you might imagine, this was created by having some issues trying to deploy. So I welcome your comments and suggestions to make this Dockerfile a bit simpler, and I'd love to learn from all of you on some best practices for structuring these Docker files as well. The last thing that I had to do to get this to work was change it from the default port, which was either 8000 or 8080, I can't remember which, to 7860. I exposed both port 7860 and then specify it here, went for the entry point of the application. I'm not sure if this was explicitly necessary. Again, this was from trial and error, looking at some of the Huggingface documentation as well. So we have this Docker file here. Now we're ready to take this, as well as the Plumber API, and one other file to go and deploy our model on Huggingface. So that is, we need going from top to bottom in the list here, the Docker file that we just spoke about, the plumber.r to create the API, as well as the Vetiver rmv.lock file. So this is another file that's created when you write the Docker file. This specifies all of the packages that we need, and it is used by the Docker file to recreate the environment that we were developing in locally. We can go to look at the specific deployment here. And there was a bit of a funky thing where the default location, it looks like this is failing. It in fact is not failing. If you come down here and go to the embedding location, and then we specify the docs like this, you see that it is in fact working. So this is what we would expect this deployed API to look like. We can make sure it's alive by trying the get, basically a ping message. It's telling us that it is in fact online, and we could come in here and use this to make some of our own predictions if we so chose. So there's a better way for us to test out this API that I'll show you in just a moment. And let me also jump back to what we had here. So I have a separate video talking about Hugging Face spaces that I'll link down below and encourage you to check out if these are new to you. But basically what we had to add here was this Docker file, the plumber.r, and the Vetiver rmv lock file. One other change that we had to make, we actually don't need this folder that I have in here anymore. I was able to, I started using this local version, but that's why we ended up having the model hosted on GitHub. So again, all you need is the Docker file, plumber.r, Vetiver rmv.lock, and all of these are created by the Vetiver package. And then you tweak the README that's generated by default when you create this space. So we have, I renamed the Penguins Model API, and then I did specify the app port down here as well. So those are the important changes that I made from default. If you're new to these spaces, I'll just very briefly show you the steps to go in and do that. Of course, you want to give it a name. We'll just say the MIT license. Select Docker. You can select. You can do blank. You can do a blank one if you'd like, and then go ahead and create this space that'll have pretty minimal components to it, that you can then add those files again that Vetiver is creating for you. So relatively a easy process to deploy this model. So now I want to jump back over into our, oops, seems like I might have lost our presentation. There we go. So we're back in this now. So we now have a deployed API. The next step is to actually use this model. And we can do this with a admittedly pretty minimal Shiny app. Just to talk through the main components here. Of course, we need to load the packages. We want to specify the endpoint. So this is the Hugging Face space that was created. And then we need to add the /predict to specify that prediction endpoint. The UI here is just all about selecting the inputs to the model, so species, bill length, bill depth, flipper length, body mass, and then we just have a button to make the actual prediction. I'm using the BSlib package to make it look a little bit nicer defaults, and then we just very simply use verbatim text output for the model itself. The server function is not very complicated at all. We specify our new data using all of the inputs that I just spoke through, and then you can actually make the predictions by using the predict function. So predict endpoint, so that was the endpoint that we specified up here, and then just pass your new data. From that, you can get the prediction directly. Let me actually jump over to the Shiny app in action so you can see it for yourself. Well, we have all of the inputs down here. I'll just make a couple of changes. So let's select Gen 2. I don't know, maybe tweak these a little bit. Click predict. And of course, we're going to get some kind of error because I'm trying to do this live. Let me jump back in here. Try predict again. Okay, there we go. Make sure there wasn't something weird about Gen 2. Maybe I misspelled it. Or maybe they're just... All right. Huh. Looks like there might getting some sort of server error there. I'm not sure what was going on with that, but you get the basic idea. This might be an artifact of using all of the free versions of these, but if you happen to spot an error yourself in this, maybe I misspelled the penguin species or something like that, I would very much appreciate your feedback and suggestions on what was going wrong with this. So let's jump back in and see. Okay, seems to be working okay. Again, maybe that's an artifact of using some of the free versions of the software here. And I have covered deploying a Shiny app to the Huggingface spaces in a previous video. So please reference that for some instructions on how to use that. It's a fairly easy process as well, somewhat similar to deploying the API itself. So now we've covered the model creation, model version control, model deployment with an API, model consumption with a Shiny app. One of the last parts, let me jump to there we go. One of the last parts that we need to cover here is model monitoring. I have a bit of a contrived example since I just deployed this model. It's not like something that's been live for a bit. But if we just add a training date to the penguin samples, to the penguin's training data that we have been using, we can simulate some model monitoring over time, where we look at the overall performance, the classification exercise as a function of date. And there's some nice functions here like Vetiver compute metrics that makes this classification quite easy for us. And Vetiver plot metrics from those metrics we just created on the previous slide. We can get a sense of the changes using some standard model outputs like accuracy, so we can see how the model is performing over time. This could be an easy way for you to pick up model drift if you're monitoring the trends of your overall model performance as a function of time. As is pointed out in the I believe it's the Tidymodeling with R book, it can be quite easy for you for these models to fail silently. So building in some of this model monitoring is a critical component for success. Okay, so thinking back to this overall workflow that I've done so far, a couple of improvements that I'd like to make myself, or maybe have contributions from all of you for the future. The one, of course, is I flew through all of these giant topics, so deeper dives would be interesting, but maybe some more specifics. I would like to build a less bloated Vetiver RM file. So I didn't show it in the video here, but it takes about 10 minutes or so for the Docker container to build. One of the big reasons for that is I have way more packages specified than need to be for a successful model. The second is I would love for these Plumber and Docker files to work out of the box. If you're like me, you're not particularly comfortable editing some things like a Docker file. I'm heavily reliant on ChatGPT for some debugging help for those. That's not a place I love to be. And so I'd like for these to work using those built-in functions. And I'm very open to suggestions to all of you for how to do so. The last is the model monitoring that I have is kind of a minimal version here. So I certainly would like to improve upon that and would welcome any of your suggestions to do so as well. Okay, the whirlwind is done. What part would you like to hear me talk more about? I know I covered a ton of topics there, each probably worthy of their own series of videos in their own right. So let me know what you liked and what you'd like me to talk more about. So thanks for joining me here today. It would mean a lot if you subscribed, if you enjoyed what I was covering today. And I'd also love your feedback on this slightly different format using the Quarto to walk through some code rather than you watch me type it out. Do you like watching me type it out? Please leave it below in the comments to help me so I can make these videos even better. So thanks so much for sticking with me, and see you in the next one.